Okay, so now that we've talked about what the Canadian traveler problem is, so just as a reminder, we're given an input weighted graph that's undirected. The weights on these edges are non-negative, meaning they can be 0 or greater. And I would like to compute a shortest ST path. However, a part of the input is what we call the trap edges. These are edges that we cannot cross over. However, we don't know where the traps are, except we know that there's at most k of them. And we only uncover or discover them when we actually run into one of the two endpoints of the trap edge. So I'm going to present you our first strategy here. So this is so the first strategy we're going to try. So this is our first strategy. And I'm not going to say that this is the most natural thing to try. It's going to sound like something like if you ever watch like a 90s cartoon, like a 90s kids cartoon, and you have it the show like, oh, how are we going to get out of the house? And the first thing that they say, oh, well, let's just go this way. And then you have the one character's like, hey, everybody now. Hey, everybody now. Stop. We're going to do this. This sounds exactly like something that would come up with that, okay? So here's the first strategy. It's going to be what we're going to call the reposition. This is going to be what we're going to call reposition. So this is going to be the reposition strategy. So remember, if we encounter, remember we know how to compute a shortest ST path. We could use Dijkstra's algorithm to do that, for example. However, if we discover a trap edge in that process, keep in mind there may be more trap edges we come across that get discovered, but we run into one that requires us to stop. To say, hey, look, we can't go any further because we can't cross over the trap edge, right? What do we do? So I'm going to describe the algorithms in this way in the scenario that this happens. So just presume otherwise, that we're just going to try to compute the shortest ST path unless otherwise stated. So I'm going to describe to you what we're going to do whenever we hit a trap edge. So when I say hit a trap edge, to be a bit more precise, it means that we've uncovered a trap edge and we're being dictated to go over it, but we can't. Is that clear, everybody? Because we're smart enough to know not to go over a trap because we might fall into a pit. You don't want to know what's at the bottom of that pit. I probably spent like 10 cents on it. So the first strategy is as follows. So if the traveler if the traveler is stuck, so I must stress when I say stuck, it just means that you simply cannot continue along the path. Meaning that you're instructed to go across it because you computed like an ST path, and you just can't because there's a trap there. If the traveler is stuck at a vertex U, at an edge E, with a trap, travel back. So travel back to S along the path at the path traveled to reach E. Then next travel the shortest ST path without using E, and all other known trap edges. So let's put this in plain language, okay, everybody? So what's going to happen is you try to compute the shortest ST path. If you stopped at a trap edge, because first you uncovered it, but at the same time you're being instructed by the shortest ST path to travel over it, you stop there, and what the reposition strategy says is you're going to return back to S. So you're just going to follow backwards along the pathway you came. And then you're going to recompute a shortest ST path without using that edge and all other known trap edges. So does everybody understand the strategy? So essentially, every time you botch finding T, you're just going to go back to S and recompute a shortest ST path without using any of the known trap edges. This should at first sound very intuitive. After you remember, if there's no trap edges, you can compute a shortest ST path, and that will get you well, you could use Dijkstra's algorithm to do that, right? However, if you know about traps, you could just simply ignore those edges and just compute the shortest ST path. However, we incur a cost, right? Where's the cost of doing this? Remember, I don't know where the trap edges are until I run into them. Well, what does the strategy tell me to do? It tells me to go back to S, right? So you're going to find that, as we're going to see in our example here shortly, is I get to that vertex where I get stopped, I have to go back to S, and then I have to go and find another shortest ST path. So you're going to find that this strategy, you go back and forth a lot. But this is why I say it's a little counterintuitive at first, and it sounds like something that the brainy 90s kids cartoon character would point out. Because remember, what do we know about the K Canadian Traveler problem? How many traps are there at most? How many traps are there at most? So this is going to be a very important integral part for how this works. So how many are there at most? So for example, if I knew there were 3 traps, too many. Say if there was only 3 traps, do you see how if I was stopped at 3 traps, I'm guaranteed on the 4th attempt that I'm going to find T, right? So there's a very nice property that exists here, is that I could potentially get stopped at K traps, and because the graph remains connected, even if I ignore those trap edges, I can still get the T. But I've eliminated needing to use any of those trap edges. So that's actually how you can ensure that this approach always will lead you to finding finding an ST path. I shouldn't call it a shortest ST path anymore, because the path that now you're computing is going to probably look like this. It's going to go back and forth, potentially, and it'll eventually get the T. So let's do an example. So I'm going to use the same map that we had before. I'm going to lay out some traps in here. So we're going to use the same graph that we had formulated at the beginning. So remember, that's the teleporter room. We got 1, 6, 7, 1, 1, 1, 2, 9, and 8. Got to label the vertices as T, 1, 2, 3, 4. Okay, so now we're going to try using the reposition strategy to get an ST path. So remember, earlier we established how we could find a shortest ST path in this example here. So remember, we use the following. We go along this way, right? We go up the stairs, we take the fast track, we go down these stairs, we go up those stairs, and we take the teleporter to get the T. Right? That was the shortest ST path that we had. However, I haven't put the trap edges in, right? You don't know where the trap edges are, right? However, I'm going to show you where they are just so you can see where exactly they're going to be sitting. So the spooky hall is going to have a trap edge. The teleporter room is going. The teleporter room's our teleportation here This is also going to have a trap on it, so you can't use the teleportation machine. And of course, you can't take the fast track either. Excellent. So now, do you see how quickly we cannot just compute a shortest ST path if these were the trap edges? We can't go from S to T using this path because we'll encounter at least one trap edge. So let me show you how the reposition strategy would take our traveler. So what we would do is the traveler would first follow along the shortest ST path, right? That's what we established. We'd take the shortest ST path. And keep in mind, before we get going this way, we would discover this trap edge because we touch one of the endpoints, right? So we discover that first, this one right here. But we're not going to go that way, right? We go to vertex 1. We touch one of the endpoints of this trap edge so that we discover it. That means we stop here, right? Because we can't go across the trap. So the reposition strategy says, hey, look, instead, now you're going to head back to S. So now go back to S, and you're going to compute a shortest ST path without using the known trap edges. So now we got to compute another shortest path, right? So let's compute another one. Let's get rid of the red here. Because we know that we're probably going to have a different path, right? So now, if we take this approach, what's the next shortest path? What's the next shortest path? So remember, we've discovered this trap edge and this trap edge, so we cannot use the ones I put check marks on. We can't use them. So compute the shortest ST path now. From S to T. So we got S to T. So we know we can't use these two edges, so we know our original shortest path will not cut it because the traveler couldn't go that far. Well, let's see. Let's try to use our idea we had before. So the vertex that is closest to S right now, without using trap edges, is this vertex, right? So we know that we're going to probably go this way, right? And of course, if I want to go to the next closest one, well, notice there's going to be no way, you know for sure, if I use this as part of my shortest path, we're going to run into this trap edge. However, it doesn't make any difference right now. We don't know it exists, right? We don't know that that trap edge exists. However, I will tell you that the next shortest ST path, the one that does not use the edges that I checked off there, is actually going to go up this way, to T. It's just going to go through the maze of doom. So taking a beeline right through the maze of doom is the next shortest path without using these two trap edges. Does everybody see that? But now you'll notice that the traveler now has a route to continue the path. Okay, let's go. So next, now the traveler is now going to go back to vertex 1, and it's going to go across to T. So the traveler reaches T and has not used any one of those trap edges. Does everybody see that? So you'll notice that all this is doing is just resetting the search every single time. So what's the length of this path? So it is 1 to get here, then 1 to get back, right? So 2, and then 1 to get to 1 again, so 3, plus 8. So 11, right? Yeah, because we got 1, 2, 3, 11, right? So that's the length of this path. However, notice that in this case, it's pretty nice. I didn't have to go back and forth a whole lot. I'm going to show you how bad this gets in the coming moments. But is the reposition strategy clear to everybody? So you're just going to, whenever you're stopped, so you start off by computing your shortest ST path, you're going to try to follow along that, so the traveler will take that route. Whenever is stuck, so it cannot cross a trap edge that is discovered, keep in mind that you would never use a trap edge if you knew it was there, right? What you do is you travel back to S and you just continue this process without, so you just reset it. Hence why we call it reposition. I just go back to S, I compute the next shortest path without using the trap edges I know. That's why it's called reposition. I'm gonna have the pseudocode for it in the notes. But one thing I want to point out is that if ever, like I mentioned earlier, the pseudocode in the notes will use a set data structure, but you can easily modify it so you just label edges that you discover as trap edges. But I leave it more as a remark. Now, you might ask, Dan, how good is the reposition strategy? So let's talk about that now. So I got a theorem that we're going to prove that is going to show how competitive this algorithm is. So we're going to prove this together, everybody. And you're going to find that this is actually a really slick way of arguing this. And it follows the intuition I gave you over there. Is that there's going to be a possibility we're going to have to go back and forth a whole bunch of times. And I told you how many times that's possible. So here's the theorem. So this was proven by Westphal in 2008. So I'm just going to refer to the whole algorithm. This is just what you would use in the algorithm. I'm going to refer to it as the reposition algorithm. The reposition algorithm is 2k plus 1 competitive for the K Canadian traveler problem. I'll just abbreviate it as CTP. So we're going to try proving this claim together. And it's going to follow the exact intuition I just gave you, that how many trap edges are there? There's going to be at most k of them. So it means that we're going to have to go back to S how many times at most? Well, I'll let you think about it. Let me start writing this down. So observe the traveler can fail to find T and return to S no more than k times, right? Because there's k trap edges that you could potentially run into. You could discover them but never traverse over them, but this is the upper bound on that. No more than k times. Then the traveler successfully moves the T using a shortest ST path with no trap edges. Right? That's exactly what we said earlier. So this is the key observation for the setup for this proof. Is everybody okay with this so far? So this is going to be a key part to how this works. So I'm going to formalize this now. So if you understand this setup, that means I'm going to go back, return, back, turn. So I'm going to be going to I get stopped at some vertex at most k times. I'm going to give this a name. I'm going to call it B for blockages. blockages, or boo, trap. So we're gonna give names to all of these paths that I attempt to use, and then to get the one that's successful, okay? And then we're gonna try to use this information. That is, the algorithm computes B, which is gonna be at most k plus 1, shortest ST paths, which I'm going to give them names, P1, P2, all the way up to PB, where the first B minus 1 fail as the encounter trap edges. So I'm going to give the trap edges names. E1, E2, all the way up to EB minus 1. And the last path PB, reaches T in a graph using edges. So it's gonna use edges. So that graph is gonna contain the edges E. Those are the ones that we have in our graph. Where I remove, this is what the set minus means. That set minus, I get rid of all the trap edges that I found. Right, that's what it does. That's what the reposition strategy does, right? So this is just a formalization of this. So now that we have that information, I'm going to formalize sets that are going to represent what the algorithm has as information about the trap edges at each time during the execution of this algorithm. And I must stress, the reason why I wrote it as B is because it could be the case that the algorithm actually doesn't go and encounter all K traps, right? It could happen earlier. But we're going to need this helpful bound for when we try to figure out the competitive ratio. So now I'm going to define I want to define what the current set of edges will look like. That let the edges in G when computing P1. Remember, that's the first shortest ST path that's used. We're going to call that E1, which is going to be the set of edges because there's no traps that have yet been encountered. Then, for paths PI, where 2 is less than or equal to I is less than or equal to B, let EI, so remember these are going to be the set of edges that I'm using to compute that shortest ST path at that time for that path. It's going to be the set of edges in E such that E is not in E1, E2, all the way up to EI minus 1. My spider friend, you're getting in the way. So essentially, and this makes complete sense, right? So let me write this in plain language for our proof, okay? So notice P1 contains edges in E1 where E1 is in the path, right? Remember E1, this lowercase e1 that's the first trap edge we're going to run into. That's in the first path that gets computed. P2 contains edges in capital E sub 2, where the second trap edge encountered is in P2, and so on, until path PB contains edges in EB, in capital E sub B, but sends, sorry, that E is looking a little sad there, but sends the traveler to T successfully, right? So this is all just fancy M-word business, mayonnaise, as we all know. That is all it's saying is, every time I compute a shortest ST path, every time I fail, there's going to be less edges I have available to me to compute the shortest path. That means that the true shortest ST path, if I ignore the trap edges, like as if like I literally keep the edges in place, even if they are trap edges, I just ignore the fact that there's traps. Like maybe I have a levitation ability to hover over the traps, say if they're all pits. Every time I remove one of these trap edges from my choices, can I compute a shorter path? Is that possible to compute a shorter than the shortest ST path that I get when I first compute a shortest path? Not really, no, because if I attempt to find another shortest ST path, it's going to be probably the second shortest, right? At worst, right? It's going to be at least, it's not going to be any better. It's always going to get worse. So that gives us our key observation. Observe that the set of edges in E1 is a superset, meaning it contains more, it has an edge that differs from E2, but it has all the edges in E2. And so on for all of these sets of edges. Because remember, each one of them, I take away a trap edge, right? That's what it says. So all this fancy stuff is just saying, hey, look, I remove a trap edge. So the trap edge is gone. That means that I potentially, if I try to find another shortest path, it's going to be using one, it's going to have one less edge in it, right? But it has all the other edges. So we go from more general to more specialized as I remove edges, because they're trap edges, right? And these are what I'm using to compute shortest paths, right? So what does this mean? That means that the length of P1 is at most the length of P2, which is at most the length of P3, and so on, all the way up till it's at most the length of PB. So this is going to be our best friend here, okay? So let's watch this. Then the length of the path computed is at most the following. Now remember, whenever I fail to find T, I went to some vertex, then I come back. You'd agree with me that if I just capture the length that it takes me to get to the vertex I stop at, if I include the other edges that would get me to T if no trap edges were in my way to prohibit me, that serves as an upper bound on how long the trip would be to get to that vertex, right? So we're going to use that information for some of our little bit of algebra here. So watch this, watch this. So we're going to now derive the competitive ratio. So all it's going to feel like is I'm just going to take the information we just laid out, and we're going to see that all we have to do is just kind of put a little cherry on top, just to point out what the optimal is. And that's the cutest part about the proof. So watch this. So I'm not going to tell you what the cherry on top is. I want to save that. So I'll let you just pick it up and just put that thought in the back of your mind just for now. Just like a feather, just put it in the back behind your ear, or like a pencil. Just keep that there for now. So let's measure out using that observation I just pointed out. So I have an attempt to find t and I fail, right? So that could be no more than the time it takes me to get to that vertex stopping. But I'm going to include and compensate by including also the rest of the length of the path that gets me to t, but it obviously can't get there. So imagine I give you some path pi. So this is just going to be the distance it takes for me, and possibly more. So it failed to reach t in this one attempt. And then, of course, what does the reposition strategy do? You go back to s, right? Which surely cannot be longer than just the length of pi, right? So you return to s. But how many times do you fail? b minus 1 many times, right? So that's capturing all of our failures, right? So all of this is just our attempt to find t, and we fail, right? And then lastly, at the end of this process, after we've done b minus 1 many of them, we end up with our actual last attempt, which is going to find t. And that's the length of the path, the last path that we use. But here's the catch. Here's the catch. Based on the inequalities I have over there, I can replace each one of these pi's with pb, because the length of pi for any one of the i's except for pb, all of them have to be either the same as pb's length or is pb, right, in the length. Because it only gets longer, right? So let's figure this one out. So notice that this is just 2 times 2 of these, right? So I just have 2 of those, so I'm just going to rewrite this. So this is at most the sum of 2 times dpb from I is equal to 1 to b minus 1 plus the length of pb. But how many of these are there? There's b minus 1 many of these. So you end up with b minus 1 times 2 times dpb plus dpb. Now, you can do a little bit of algebra here. And once you've done that, you end up with this being simplified slightly. You end up with 2b minus 1 times dpb. Now remember, I told you that b is at most k plus 1, right? So I'm going to put k plus 1 in wherever I see b. And now, notice that 2 times k is 2k. We got 2 times 1 is 2. So I have 2k plus 2 minus 1. So I end up with 2k plus 1. This is 2k plus 1 times dpb. Now here comes the best part about this. So let's talk about what the cherry on top in this proof is. I haven't told you what the optimum is at all. Does anybody see what the optimal solution actually is? So think about this very carefully. Very carefully, everybody. Think very carefully. What is the optimal solution? So remember, for the b minus 1 attempts, they all fail because they encounter an edge. remember, each one of them is a shortest ST path, right? Then the last attempt is the shortest ST path without using any trap edges. So what is that then? What is PB actually? Well, here's an observation. I would recommend writing this as a proper sentence, but here's an observation. That the optimum is actually equal to the length of PB, because this is the length of a shortest path without using any of the trap edges, right? That's what it is. There's your cherry on top. Because remember, PB was a shortest ST path. It doesn't use any trap edges. And keep in mind, it doesn't have to be exactly PB. It could be another path of the same length. But here's the catch. That means that the competitive ratio has to be as follows. It's 2k plus 1 times dPB over dPB, which this is exactly equal to 2k plus 1. And we're done. So now we could say that if we have at most k traps, the reposition strategy, when you formulate it as an algorithm that recomputes shortest paths, as I have in the notes, what you end up getting is a competitive ratio of 2k plus 1. So if k is, for example, 1, then you end up with it being 2 times 1 plus 1. So that means it's 3. So it's at worst 3 times the length of an optimal offline shortest ST path. So it means that if you didn't have all that information, that's how far away from the optimal answer you're going to get. Is that clear, everybody?